The question is, how do we determine if something is polar or nonpolar? And as usual, we're going to write the Lewis structure first. So water, we're going to count the valence electrons. 2 hydrogens. Each hydrogen has 1 valence electron. And that gives us 2. Plus 6 for oxygen gives 8 valence electrons. And to draw our Lewis structure, we're going to do the skeleton. Oxygen goes in the middle because it makes more bonds and is more electronegative. And then with our last 2 electrons, we get this Lewis structure for water. Now to do the 3D shape, it's a little tricky. There's a couple ways to do it. But first, it's best to realize that this is AX2E2. And with 4 things, that's going to be about 109.5 degrees. So the way that works is we do a lone pair on oxygen. And I'm going to show the lone pair a little bit different this time. I'm going to show one going back and then one coming toward us. That's kind of nice to do it this way. You don't have to do it, but that way we can see our hydrogens are actually going to be in the plane of the board or the screen here. And this angle is less than 109.5 because these lone pairs take up more room. They look kind of like a little alien ice cream cone now, but that's okay. Now to determine if this is polar or not, there's 2 things we can do. We can remember Funkelbrich, which is our most electronegative atom, fluorine, and our least electronegative atom, hydrogen. And because oxygen is so much more electronegative than hydrogen, it's going to pull electrons over toward it. So if we draw an arrow from the less electronegative atom to the more electronegative atom, sometimes we put a little plus down here next to hydrogen because it's less electronegative, and then another arrow like this for the bonds, both of those arrows are pointing up toward the oxygen, which means that's going to be the side of the molecule that is the negative side, and the hydrogen side is going to be positive. Another way to show this is with the little squiggly delta sign. So the oxygen gets a delta minus, higher electronegativity, and each hydrogen gets a delta plus. And if you're wondering how I knew, besides Funkelbrich, that oxygen had a higher electronegativity, I have that chart. Oxygen is 3.5 on my chart, and hydrogen is 2.1. So if we had drawn water just like the Lewis structure in a linear fashion, this would look like they cancel out, but that's why it's our 3-dimensional geometry that is so important in this. So water is definitely polar. Well, let's look at a little tougher example. From our notes. So CF4 is a question that came up, and this one's in 3 dimensions, so it's a little bit tougher. So we want to draw our Lewis structure. Carbon has 4 valence electrons, plus 28 for the 4 fluorines, and that gives us 32. Carbon goes in the middle because it makes more bonds. It's also less electronegative. When I fill in the rest of the electrons, there's 24 more to fill in. It looks like this is a symmetric molecule. And it actually is, but they're not 90-degree angles because this guy is AX4. So when I draw this in 3 dimensions, let me change colors here. I'm going to have carbon in the middle, 1 fluorine going up at 109.5 from this fluorine. And then because it's a tetrahedron, we end up getting this shape where everything is 109.5 degrees apart. And you might be asking, well, how do I determine if this is polar or nonpolar? Well, fluorine is definitely more electronegative. It's 4.0. Carbon is 2.5. So big difference in electronegativity. So with the arrows, I have one pointing up, and then these arrows are all pointing toward the fluorines. Now the question is, do these arrows cancel each other out? And the answer is yes. So even though the F on top is pulling straight up, the other three are pulling down and at equal angles. So I think of it as like triplet kids pulling on a teddy bear. And each of those little kids has one of the arms or legs, and then a parent up top is also pulling equally. So that Winnie the Pooh bear has been stretched, or you could think about Woody from Toy Story. So if they're all being pulled at 109.5 degrees apart and they're all pulling equally hard, Woody's not going to move at all. So this guy is actually nonpolar, even though he has polar bonds. So the key is Lewis structure first, correct a three-dimensional model, and then draw your arrows to the more electronegative atom. If you want to use the little squigglies, the negative sign is equally spread out along the outside. And you might remember, in order to have a polar molecule, you have to have a positive side and a negative side. Here, the positive is in the middle, and the negative is spread out equally on the outside, so it's definitely not polar. I hope this helps.